Today we shall look at differential calculus and how to find the differential coefficient of a function using first principles. Alright, now suppose we have a function of x given by y is equal to f of x, and there is a small increment in x from x to maybe say x plus dx. X has increased in value from x to x plus dx. Now, of course, we know that there should be a penultimate change in y with respect to x, because as x is changing, y is also changing. And this change in y with respect to x is written as dy dx, and is given by the limiting value as dx approaches 0 of f of x plus dx minus f of x divided by dx. The limiting value as dx approaches 0 of f of x plus dx minus f of x over dx. So this is the simple equation or the simple formula used to find the differential coefficient of a function from first principles. And remember that the process of finding the derivative or differential coefficient of a function is known as differentiation. Now let's look at some practical examples. Suppose you are given a problem like y is equal to x, and you are asked to find the derivative or the differential coefficient of y with respect to x using first principles. Alright, now what we are going to do is, remember that y can also be written as f of x, and this f of x is given by that parameter x. Alright, you're asked to find the differential coefficient of y with respect to x, the rate of change of y with respect to x. Alright, so, and that rate of change is dy dx, and is equal to the limiting value as dx approaches 0 of f of x plus dx minus f of x over dx. So what it means now is that anywhere we see x, we're going to replace it with x plus dx. So dy dx is equal to the limiting value as dx approaches 0 of what we are going to have here is x plus dx minus, remember that f of x is already given to us as x, so we're going to replace f of x with x. So we put x divided by dx, and dy dx is equal to the limiting value as dx approaches 0 of course we know we have x here, we have minus x. X minus x is equal to 0. They have cancelled out. So what we have here now is a dx over dx, and dx over dx is equal to 1. Therefore, it implies that if y is equal to x, then dy dx is equal to 1. That is the differential coefficient of the function x. Alright, now let's look at another function. Suppose you are given another function like y is equal to maybe say 3x, and you are asked to find the dy dx of this function using first principles. Alright, what we are going to do here is y is equal to f of x, and that f of x is equal to 3x, because this is a function of x. Then dy dx is equal to the limiting value as dx approaches 0 of f of x plus dx minus f of x over dx. So what we are going to do now is anywhere we see x in this particular function, we have to replace it with x plus dx. So dy dx is equal to the limiting value as dx approaches 0 of, here we have 3 into, we are replacing this x now with x plus dx, then minus, remember that f of x is given to us as 3x divided by dx. Okay, now we continue. Dy dx is equal to the limiting value as dx approaches 0. We expand this bracket. 3 times x is 3x plus 3 times dx will give us 3 dx, then minus 3x over dx. Okay, dy dx is equal to the limiting value as dx approaches 0 of 3x minus 3x is equal to 0. So we're left with 3 dx divided by dx. Now, of course, we know that dx, we cancel dx, and we are left with 3. Therefore, we conclude by saying that if y is equal to 3x, then dy dx is equal to 3. And that is the differential coefficient of 3x. Okay, now let's look at another simple example, like we'll be asked to find the differential coefficient of y is equal to maybe say 3x squared. Let's find the differential coefficient. Now, as usual, this is y is equal to f of x, and f of x is equal to 3x squared. Alright, so dy dx is equal to the limiting value as dx approaches 0 of f of x plus dx minus f of x divided by dx. Alright, so we continue. Dy dx is equal to the limiting value as dx approaches 0. In this expression, anywhere we see x, we're going to replace it with x plus dx. So it becomes 3 into x plus dx. Remember, we're going to square it. Then minus f of x is already given to us as 3x squared divided by dx. Alright. Okay, so dy dx is equal to the limiting value as dx approaches 0 of, we're going to expand this bracket first. So we're going to have 3 into x plus dx multiplied by x plus dx. Then we close the bracket. Then minus 3x squared divided by dx. Okay, so dy dx is equal to the limiting value as dx approaches 0 of, when we expand this bracket, we're going to have 3 multiplied by x times x is x squared. X times dx will give us x dx. Then dx times x will give us x dx. And dx times dx will give us dx all squared. Then we close the bracket, minus 3x squared, then divided by dx. Okay, we continue. Dy dx is equal to the limiting value as dx approaches 0 of 3 multiplied by, alright, so this is x squared plus x dx plus x dx will give us 2x dx. Then plus dx all squared minus 3x squared all over dx. Okay, now dy dx is equal to the limiting value as dx approaches 0 of, we're going to use this 3 to multiply everything in this bracket. So 3 times x squared will give us 3x squared plus 3 times 2x dx will give us 6x dx plus 3 times dx squared will give us 3 dx squared. Then minus 3x squared, that is this one, divided by dx. Okay, of course we know we have 3x squared here. We have minus 3x squared here. 3x squared minus 3x squared is equal to 0. So we have eliminated that. So what we are left with is dy dx is equal to the limiting value as dx approaches 0 of, what we have here is 6x dx plus 3 dx all squared divided by dx. Okay, we're going to complete this upstairs here. Now, dy dx is equal to, here we are going to carry out the distributive law of division. Remember that the distributive law of division states that a plus b divided by c is the same thing as a over c plus b over c. So that's what we are going to apply here. So we're going to have dy dx is equal to the limiting value as dx approaches 0 of 6x dx over dx, 6x dx over dx plus 3 dx all squared over dx plus 3 dx all squared over dx. Of course, we know that this dx here, we cancel dx. Dx here, we cancel one of the dx here. So we're left with dy dx is equal to the limiting value as dx approaches 0 of, what we have here now is 6x plus 3 dx. Alright, now remember that as dx approaches 0, we are going to substitute dx as 0 in this expression. So if dx is equal to 0, That means we have 0 times 3, and 0 times 3 is equal to 0, and 0 plus 6x will give us 6x. Therefore, if y is equal to 3x squared, then dy dx is equal to 6x. Alright, I hope that is understood. Okay, now we move ahead to look at another interesting function, like let's see a function like when we given something like y is equal to 5. You're asked to find the differential coefficient of 5. Alright, now this particular problem may seem to be so interesting in the sense that there is no x attached to 5. So what we are going to do to make our work very, very simple is to attach x to 5. And when we do that, we're going to have y is equal to f of x. And that f of x is equal to 5x raised to power 0. We have not committed any error here, because we know that x raised to power 0 is equal to 1, and 1 times 5 is still 5. What we want to do is to introduce x there, so that it will be very easy for us to determine. Now, we know very well that dy dx is equal to the limiting value as the x approaches 0 of f of x plus dx minus f of x over dx. And from here, dy dx is now equal to the limiting value as dx approaches 0 of, in this expression, anywhere we see x, we're going to replace it with x plus dx. So we're going to have 5 into x plus dx raised to power 0 minus f of x is given to us as 5x raised to power 0 over dx. And dy dx is equal to the limiting value as dx approaches 0 of, because we know that x plus dx all raised to power 0 is equal to 1. Any number raised to power 0 is 1. So 5 times 1 is equal to 5. Then minus, here x raised to power 0 is equal to 1. 1 times 5 is equal to 5. Then divided by dx. Alright, so dy dx is now equal to the limiting value as the x approaches 0 of 5 minus 5 is equal to 0. 0 over dx. And 0 over dx is equal to 0. Therefore, if y is equal to 5, then dy dx is equal to 0. That's why we normally say that the differential coefficient of a constant is equal to 0. Okay, now from what we have seen so far in these examples, we can draw a general conclusion by saying that if y is equal to ax raised to power n, then dy dx is equal to, this n will multiply x. So we're going to have a(n)x, then we're going to subtract 1 from n, becomes n minus 1. This is the formula used to find the differential coefficient of a function easily. But when we are asked to find the differential coefficient of a function from first principles, please, we need to engage this formula to do that. Thank you very much for listening. If there is any question you have to ask, please try to drop it in the comment section, and don't forget to like, share and follow our page.